this lecture, we will study about the discrete Fourier transform. Before studying about the discrete Fourier transform, we need to know the importance of time domain signals and frequency domain signals. Why we are converting a time domain signals into frequency domain signals. In time domain representation, we can analyze the signal up to a certain level, because in time domain, signal amplitude and phase both are combined. We can't separate them. Whereas in frequency domain representation, we have two plots. One is magnitude spectrum and second one is phase spectrum. So we can analyze the signal more effectively in frequency domain because of this separation. We can separately analyze the amplitude with respect to time. We can separately analyze the phase with respect to time or frequency. That is what frequency domain representation. And why we are moving from discrete Fourier transform. The discrete Fourier transform is one of the most powerful tools in digital signal processing, which enables us to find the spectrum of a finite duration signal. So here we are finding the spectrum by taking a signal with finite duration. Okay. There are many circumstances in which we need to determine the frequency content of a time domain signal. So this is what the discrete Fourier transform. So I already told you discrete Fourier transform is applicable only for finite durated signal. So we are taking only n samples of x of n and we are writing it is from 0 to n minus 1, where your small n is extending from 0 to capital N minus 1. It represents your x of n has n number of samples, or length of your sequence is capital N. And its discrete Fourier transform can be written as x of k, which is equivalent to sigma n equivalent to 0 to n minus 1 x of n e power minus j 2 phi kn by capital N. Here k is also extending from 0 to capital N minus 1. Given n DFT coefficients x of k, whereas k is from 0 to n minus 1, the related capital N time domain samples x of n, which is small n extending from 0 to capital N minus 1, can be recorded by the inverse discrete Fourier transform. And the inverse discrete Fourier transform formula is small x of n equivalent to 1 over n sigma k equivalent to 0 to capital N minus 1 x of k e power j 2 phi kn by capital N. Note that capital X of k is a function of discrete frequency index k, which corresponds to omega k, which is equivalent to 2 phi by n. So we are not only writing our discrete Fourier transform in terms of e power minus j 2 phi kn by capital N, and we are replacing e power minus j 2 phi by n with the trivial factor omega suffix n. So we can rewrite these two formulas in terms of trivial factor. One is sigma n equivalent to 0 to n minus 1 x of n omega small n k suffix capital N. So that is for discrete Fourier transform. If you want to write the inverse discrete Fourier transform to find your x of n from x of k, that is also possible, by writing the equation 1 over n sigma k equivalent to 0 to capital N minus 1 x of k omega minus k n suffix capital N. So this is in terms of twiddle factor. Okay. The correctness of the DFT formulas can be validated through, see, we need to know whether the DFT formula is correct or not. So that is also possible by writing. See, already we know the formula for x of k. We know the formula for x of n in terms of x of k. So here we are writing that in place of small x of n, we are replacing it with 1 over n sigma m equivalent to 0 to n minus 1. So already we used k. So here we are using m, capital X of m omega n minus mn. So if you write it, you will get the equation, and the orthogonality of discrete complex exponentials suggests 1 over n sigma n equivalent to 0 to capital N minus 1 omega k minus m into small n suffix capital N. So here we have one condition, omega suffix capital N, whereas k minus m into n is there. If your k minus m equivalent to Rn, if your k minus m equivalent to Rn, so we can take it as 1 or we can take it as 0. So there you will get the same formula which is related to your twiddle factor, and we can represent our discrete Fourier transform in terms of matrices also, because our omega n nk, which is twiddle factors, we can write a matrix related to twiddle factor. So here x of k equivalent to x of n should be multiplied by the twiddle factor. So here in terms of matrices, we are writing x of k to the left side, and twiddle factor matrices, if you implement the matrix, you will get 1 1 1 1, and the next row is 1 omega n power 1 omega n power 2 omega n power 3, so on omega n power n minus 1, and the next row is 1 omega n squared omega n power 4 omega n power 6, so which is multiplied version of 2, and the next row is multiplied version of 3. Okay, so in this way we can construct one twiddle matrix. Okay, and this twiddle factor also has so many properties. Omega n is symmetric, so omega n, which is equivalent to omega n transpose, and orthogonal, omega n power h, which is equivalent to identity matrix. So there we can find the inverse of your twiddle factor also, 1 over n omega n complex. So this is one of the way. This is one more way to write the discrete Fourier transform. The twiddle factor omega n and k, which is equivalent to e power minus j 25 k n by capital N, is periodic in both k and n with fundamental period capital N. So if you replace your k with k plus capital N, you will get the same value. If you replace small n with small n plus capital N also, you will get the same value. So this is about your discrete Fourier transform and some of the properties related to your discrete Fourier transform. And here we have summary of properties related to your discrete Fourier transform. One is linearity property, time shifting property. See, in time domain we are shifting our input signal, whereas in frequency domain, that is what discrete Fourier transform should be multiplied by a tweedle factor omega n nk. Next, frequency shifting. In time domain, you are multiplying it with omega n minus mk. So in frequency domain, it should be shifted by m units. That is what x of k minus m n. And the modulation. And here x of n is multiplied by cos of something. So in frequency domain, definitely it will be delayed folding property, conjugation property, duality property, convolution property. Already we know convolution in time domain is multiplication in frequency domain. So x of n convolved with h of n, definitely in discrete Fourier transform, in terms of discrete Fourier transform, we can write it as x of k multiplied by h of k windowing property. So Parshall's theorem. So here the Parshall's theorem is very important. So sigma n equivalent to 0 to n minus 1 mod x of n whole square equivalent to 1 over n sigma k equivalent to 0 to capital N minus 1 x of k square. So this is what these are the properties of your DFT. So this is about your DFT. In the next class, we'll see the remaining properties